Hey everyone, this is Matt Klooster and Bryce Furr here, and we're showing you our shell and tube heat exchanger design for MSU's Supercomputer Center for ME416. Our design parameters for this project were to cool MSU's supercomputer, which generates 1 megawatt of heat continuously. We were using water at a flow rate of 10 to the 6 gallons a day for cooling, which had an initial temperature of 57 degrees Fahrenheit. The water should not have a temperature increase of more than 3 degrees Fahrenheit. The heat exchanger should be relatively compact, easy to service for cleaning and disinfection, able to operate between potable water and working fluid, and no longer than 20 feet in length. The working fluid to be identified by us comes in a temperature between 90 to 100 degrees Fahrenheit, and the pressure drop should be minimized. Our design approach was to use Aspen 1 exchange design and rating, and then we used many different materials until the most effective material for heat transfer at a reasonable cost was determined. The cold side fluid was water, the hot side fluid was propylene glycol, and we used this coolant because it was deemed safe by the FDA for industrial food production, so if it got into the water, it wouldn't be a big deal. Different sizes and numbers of tubes and shells were used until enough interpolations were done to determine the most effective layout for the design.
Hi, this is Bryce, and I'm going to go over the process conditions we put into Aspen. On the cold side mass flow rate, we knew that, so we put that value in. Then we solved for the hot side mass flow rate, so we just left that blank in Aspen. We estimated the inlet and outlet pressures, and we found these through reiteration. We applied the cold side inlet and outlet temperatures to be 57 to 60 degrees. Our hot side inlet temperature was known to be 100 degrees Fahrenheit, and then we estimated our hot side outlet temperature would be about 76 degrees, and we also found this through iteration of the design. And we thought that a pressure drop of about 10 psi was pretty reasonable. When it came to the physical characteristics of the exchanger, we generally stuck to the defaults in Aspen, and this was because those were generally the cheaper options and the more efficient options, at least for our setup. We set the inlet for the cold side to about 14 inches. We used copper tubing on the hot side to increase the efficiency and decrease the size of the exchanger. And we did a 30 triangular tube pattern, which we thought was the most cost effective. We got a resulting length of about 18 feet, which was within the 20-foot requirement, and it was a relatively compact diameter at about 25 inches. Our design came out to be about 7,000 pounds and around $62,000, which was relatively cheap compared to the other designs that we previously had. In summary, Aspen found the tube side mass flow rate to be about 118,000 pounds per hour. The total heat exchange was about 0.293 megawatts, not close to our 1 megawatt design requirement. We probably need about 3 of these to reach that requirement.
In conclusion, it would take about 3 of these heat exchangers to perform the required duties, which is not really a feasible solution because it wouldn't meet the relatively compact design requirement. Also, cleaning accessibility was reduced in this design to account for cost in order to keep it under 70 grand. The cabin front end type would be easier to clean, but the bonnet bolted design was significantly cheaper. A couple possible suppliers we found were Thrush and Quintel.